Remember when internet cafes were a thing? All you needed was a couple of tables, some chairs, a router, and some halfway decent coffee. But now, don't you expect every cafe to have internet? What? I can't stream all 400 of my saved Food Network how to videos while sipping my latte? Ugh, I'm leaving. The same is true with security with microcontrollers these days. Doesn't include built in security? Bah! Next. This is especially true with automotive and industrial designs, where security needs to be incorporated into the very building blocks of your design, along with over the air updates, some serious compute performance, and a slew of networking interfaces. Next stop, learning how to make the perfect bolognese while driving. Wait, probably a bad idea. Hi, I'm Amelia Dalton, host of Chalk Talk. Automotive and industrial designs demand a unique set of design requirements, and you need a microcontroller that's up to the job. Luckily, my guest is Brian Carlson from NXP, and we're talking about the MPC 574 microcontroller family, which has all of this and more. And before we get started, don't forget to click that link. There you can find more information about the MPC 574 microcontroller family from NXP. Hi, Brian. Thank you so much for joining me.
Thanks, Amelia. Happy to be here.
Okay, so we're not talking about your mom's microcontrollers today, are we? What kind of target applications are we looking at here?
Yeah, so these devices, we call them the MPC 574X family. They're really targeted for automotive and industrial applications, and those applications require a lot of performance. They need embedded flash around memory.
Yep.
A key aspect, too, is security, because these applications, you don't want some kind of hacking involved because you're talking about lives and expensive equipment here. So security is very important. And also, multiple network interfaces are critical. In a vehicle, we show one of the diagrams there, being able to connect through multiple interfaces to a vehicle is important. In automation, you have to connect to multiple networks, controlling different types of equipment and monitoring other types of equipment. And then on top of that, functional safety is really important in both of these markets because, as I said, you don't want something to go wrong and that can cause some tremendous damage or injury or deaths even. So functional safety is critical. So the two markets that I mentioned are automotive and industrial. In the automotive market, one of the key applications we're seeing this in is in secure gateways. Gateways are really the central box within that vehicle. You see that white box in the vehicle diagram. All those communications throughout the vehicle are talking, all these different boxes are talking to each other through that gateway. And that gateway manages the security, so everything is communicated properly and securely throughout the vehicle. Domain controllers, those other individual boxes, we see these devices also being used in those boxes to control things within the vehicle. Telematics, which is the interface to the real world as far as wireless connectivity through your modem, through Wi-Fi, being able to control that process. And today, electronic vehicles or EVs or HEVs are starting to have connections to the outside world through the charger. So you may plug your EV into a charger. So you also need secure communications between that vehicle and the grid, that charging station. And then finally, one area that we're seeing a lot of applications in is battery management. So batteries are everywhere today. There's a lot of technology that goes into batteries to make them efficient. They have to be well managed as far as temperature, just managing that whole environment and monitoring that. So we see these microcontrollers as being very applicable to those also. So on the industrial side, it's a little bit different. It's more about control and monitoring within an industrial environment. And here, very similar though, it has lots of unique interfaces that you have to be able to support. It has security requirements because you don't want people to be able to break in or steal information. And you need to be safe. So we see this not only in industrial automation, but also security, building control, and even now we're seeing applications for AGVs or robots. So robotics, you're leveraging a lot of the technologies that are in vehicles to apply those to robotics. So there's a lot of applications for these types of processors.
Excellent. Okay, Brian, let's talk about cars first. I love that automotive stuff, and it's a huge market today, right?
Oh, exactly. It's a growing market, a fast-growing market, especially from a microcontroller or processor point of view, because today you may have vehicles that have 30 to 50 computers or processors within them, and that's growing exponentially up to 100 to 200 processors. So all of these processors, they're called ECUs or electronic control units. They all have to communicate communicate with each other in the car. And you're starting to see cars become autonomous or self-driving cars. That drives even more compute power within the vehicle.
Sure.
All those boxes have to communicate each other. The smart brain that's looking at the vision, looking out to understand what's going on, it has to talk to the brakes to say, I'm about to hit something, slam those brakes on. So all those have to communicate. So the gateway is becoming a very fundamental, very crucial part of the automotive systems. And it really enables that cross-domain communications between the different ECUs or boxes within that vehicle. So gateway has to have central computing. It has to have lots of security. Again, we don't want hackers to be able to break in or manipulate it. You also want to be able to do over-the-air updates. You want to be able to update this in the field. So once the vehicle goes out, instead of doing a recall, maybe I want to be able to update that firmware in the field. They don't have to come in the shop.
Yeah.
Maybe new features. There's a lot of things that over-the-air update can enable. So in this application, we have lots of different interfaces. We're seeing Ethernet really coming into the vehicle very quickly now. So Ethernet is kind of the new interface, lots of high-speed data because of these new features, autonomous driving features or driving assistive features. The infotainment system with all the audio and video, it requires lots of data, so Ethernet becomes a critical interface. The traditional interface within cars is called CAN or the newer CAN FD. This is the controller area network. So you need to have a lot of these interfaces too to interface to the different boxes, as well as FlexRay is another interface, and LIN, which is a slower interface, really connecting to things like switches and basic things within your car. On top of all those interfaces, you need to have storage. I talked about the over-the-air updates. You need to be able to store those and to be able to program the various parts within the vehicle. So you need to have storage, so support for some kind of memory like SD or eMMC storage. And you need to have lots of flash memory for execution and SRAM for high-speed execution. On top of that, security is very critical, as I mentioned. So you need to have a hardware security module, which ensures that this is a trusted system. It's very secure. And because of all the features that a gateway has to do, it has to have a lot of performance. And that's where multi-core processing comes in.
Okay, so we talked about how this is central to the communications in the car, but is it applicable in other areas in automotive design?
Yeah, great question. As I said, automotive is growing very quickly. There's a lot of different processors in these ECUs within the vehicle. And another area that we're seeing that this device is being used very much is in what's called body domain controllers.
Okay.
And a body domain controller is something that interfaces with everything you use within your car. So when you're turning on your air conditioner, or you're opening your door, or you're approaching your vehicle and you unlock the doors, for example, or you have different motors to slide the windows up and down, the lighting of your car, adjusting the lighting, turning the lights on when you approach, or turning the headlights off after you leave the car after 30 seconds. All these functions, there's a lot of stuff that goes on within that vehicle. So this is where a body domain controller comes in. It's responsible for all those things that the driver and the passenger see within the vehicle. So it supervises the car status. It actually has to run while the key is in, the ignition's on, when the car is stopped. And surprisingly, a lot of people don't realize when you park your car and you walk away, you take that flight, your car actually has this body domain controller running all the time behind the scenes. The important thing there is it has to be very low power or it's going to drain the battery.
Sure, yeah.
So low power is very critical for this. So we'll talk about that later. So a key in these applications is you have to have lots of different interfaces. You have to interface to that CAN bus I talked about. A lot of those interfaces are within the body domain. The LIN, some of these are very low cost, inexpensive interfaces called LIN, talking to your door modules, for example. And then there's a lot of analog types of signals that come in related to the lighting and other aspects of the vehicle. So you have to have A to D converters and timers to control what's going on in the vehicle and sequence things at certain times, or potentially pulse width modulation outputs. So there's a lot of analog and timers that are also needed for this application. And then from a safety point of view, I've talked about functional safety. In an automobile, these are typically called ASIL B, the second level of safety within an automobile. And it has security also, because you don't want someone to be able to break into your mirror, for example, take off your mirror, connect into that wire, and be able to control your car remotely somehow. So security is always a fundamental thing that you have to support in these types of applications. And then finally, it has to do a lot of workloads. You need large flash memory to support all those different functions, all those algorithms that control the motors, that control the lighting, the air conditioning. You have to have sufficient flash memory to support all of those applications.
Sure. Okay, Brian, let's talk about that industrial business. Now, how is this being used in industrial applications?
Yeah, there's actually a lot of similarities. So we'll start off with the gateway application. This is where fundamentally it fits very well in industrial automation because in an industrial environment, you have several different types of subsystems involved. There's lots of sensors, there's different types of controls and motors, actuators. There's also things like visual audio indicators where you need to show to the users kind of a human interface to this machine of what's going on. So what we're seeing is within the industrial automation, they're actually using this automotive interface that was developed back in the mid-90s called CAN bus. So we talked about CAN being used in the gateway within the automobile. We're seeing it also being used within industrial automation.
Okay.
So this automotive kind of focused device initially found a home in industrial automation because now you have these CAN interfaces. There's also Ethernet that goes out to more of a central control unit, a server, for example, that kind of oversees the whole system. But this gateway device is enabling that secure communications and control between all of those different subsystems within an industrial automation environment. So that's why it really is a key central component also, much like the automobile in industrial automation applications, and it provides that security with the hardware security module I referenced earlier. So this is a secure system. And I think within industrial automation, that becomes even more important because if you think about this, there's interfaces going all over the location. So there's more opportunities for someone to intercept that data to be able to either steal the data or to maybe hack the data and cause damage potentially. So security becomes really important in this application also, and that's why hardware security is a critical feature of a microcontroller in this application too.
Sure, that makes sense. Okay, so automotive check, industrial check. Brian, what other areas could this be used? I think you mentioned battery management, is that right?
Yeah, it's an interesting application. And this microcontroller, because of all the processing, the security, the safety, all these features, it actually is being used in a wide variety of applications. One of them that I'm seeing a lot of interest in, and people are using this in batteries to manage those battery packs. Battery technology is very sensitive. You've heard about the issues with batteries exploding in the past, if it's temperature, overcurrent, all these things have to be monitored and it has to be modeled. So what we're seeing is a need for a microcontroller like this that is very safe, that can have the performance, that can support all those various algorithms that are going on, that are looking at the state of the charge, the state of the health, the state of the life, and understanding really what's going on with that battery pack. And you have to look at a lot of different parameters like the voltage, the temperature, and balancing the cell usage. There's a lot of communication actually between the battery pack. You think that, it's just a dumb battery, it's just supplying power. Yeah, so there's more to it. And that's what this microprocessor can do. It can do all that smart intelligence behind there. It has the interfaces to communicate with it. It has the ASIL B support again, which allows to have this functional safety. You don't want this to explode.
Right.
Yeah, if anything goes wrong, you're in good shape there. And again, it has the memory. It needs a lot of memory, all those different control algorithms and monitoring algorithms. Again, safety. You want it to be safe and secure, and to have the performance to run all of those applications to monitor and control that battery connection. So this device also fits very well in an application like battery management that needs all those applications and processing, security, and safety. So you're seeing the kind of the same trends over and over of where this device fits really well in the market.
For sure. So let's get under the hood and talk about some details of this bad boy.
Yeah, excellent. So again, the family is called MPC 574X, and we actually have 3 different flavors. We'll talk more about that later. The B, the C, and the G. So this is a family of devices. So that's very important that we have pin-for-pin compatible devices depending on what your requirements are for your system.
Okay.
So some of the key pillars I would say are performance. And a lot of these applications become very intense, maybe not individually on a specific task, but maybe there's lots of tasks that are being done, like that body control application where I'm controlling the lights, I'm controlling the temperature, etc. within the vehicle.
Sure.
Lots of things going on. So what we're seeing is the need for multi-core processing. So you can dedicate one core to be doing some functions, another core to be doing other functions. So having support or the ability to have multiple cores running in parallel becomes very important.
Yeah.
So this family supports that. Another key aspect is designed for low power applications. So some of these things are running in the background. You don't want to burn a lot of power. I talked about the body application where it has to run when your car is off. When you're not even in the car, it still has to be running and monitoring things.
Yeah.
So it's designed for low power. We'll talk about that also. And I did say this is a family. It's a scalable family. It's scalable by performance, by features, interfaces, and even package type. So we have different types of packages that go with it.
Nice.
So that is the first pillar, the performance. The second one, it's about the communications. And we're seeing it in these applications like automotive and industrial, a variety of types of interfaces. The two key ones we see the most of right now are the CAN or CAN FD and the Ethernet. So we have support for all those, as well as some of the other interfaces that are used in vehicles like the LIN, the MOST, mainly for multimedia systems, and FlexRay. That's used sparingly in places like Europe today still. That's used for more real-time control of steering, real-time systems within the vehicle. So it has all of those different interfaces to support these types of applications, both in industrial and in automotive. Ethernet front, it has actually an option for an internal switch. So we have 2 ports. So you don't have to have an external Ethernet switch. You can bring 2 Ethernet interfaces directly into the device. So a variety of network interfaces are provided. And then the next area is OTA updates. So OTA is over the air, and we're talking here about the firmware which is in the device. So once you put a product out to the field, whether it's an automobile or it's a device sitting on a factory floor, you may want to update that in the future.
Sure.
These are long life types of products. So you may want to add new features. In an automobile, you may want to add new capabilities and potentially even charge more revenue. So a car manufacturer, for example, could add additional features, aftermarket features, make additional revenue. They don't have to, just when they sell the car, they make their money. They can make money later. It's also useful for critical updates. So if you want to find a bug, a lot of these systems are very software intensive. If you want to update your software to fix a bug or add additional security or address any kind of security issue, you could do that through OTA. Now, finally, on top of this, safety is another common theme I talked about. So these devices are designed to be compliant with ISO 26262 ASIL-B systems. From a security point of view, there's an integrated hardware security module that provides very fast, because it's hardware accelerated, and very secure processing and key management storage. And on top of that, as I mentioned, you have to have a long life for these types of markets. So we support, a long time, 15 plus years.
Yeah, at least, right?
I think the average vehicle on the road today is 11 years. So so that's an issue. So NXP, one of our differentiators, is supporting longevity, 15 years plus. So 15 years minimum, we typically keep going and going, but 15 years plus. And that falls under our Safe Assure program that I'll talk about later as far as the safety and longevity.
Okay, so Brian, what is this microcontroller family going to buy me as an engineer? What are the key attributes we're really looking at here?
Yeah, so there's 3 real key areas. I think the integration really stands out because you have that multi-core processing, so you can distribute the task and do multiple workloads in parallel. That's very important. It's deterministic. You have a lot of peripherals, all those different interfaces I talked about, the CAN, the LIN, the FlexRay, the Ethernet. All of that allows these devices to connect to multiple networks and really be a workhorse to connect multiple systems together. And then finally, in this integration level, it integrates all the flash and all of the RAM. And this family has a range of 2.5 meg to 6 meg flash, so very significant amount of flash, as well as system SRAM, which is range of 256K to 768. And I mentioned we have a range of packages too. We have very low cost 100-pin QFP packages all the way up to 324 BGA packages for those applications that need more signals, need more trace debug capabilities. Those could be used for development purposes and maybe moved down to a smaller package, for example. But a fundamental thing about these devices is that they're very highly integrated system-on-chip devices. Now, we talked about low power. So low power is very important in a lot of applications because you don't want to draw the battery down, especially if it's sitting there for weeks while you're flying off to Europe or a business trip. You don't want to come back and your battery's dead.
Right.
So we have to do a lot of things to support low power. So we have a dedicated core called the Z2 core. It has its own SRAM. It has a subset of peripherals that allow the system to still be operational. It's talking to a CAN bus. It can be monitoring very low power, what's going on within the system. There's an analog comparator, which is monitoring different analog signals in the system. And finally, support for what's called pretended networking, which is an interesting term. Basically, it sits on a CAN bus, and it is basically asleep looking for various specific messages or activity on that CAN bus that says, hey, wake up. So I'm sitting there very low power in a standby mode. I can be doing some minimal operations, and I can be woken up by the interfaces like this pretended networking on the CAN. So the combination of all this allows that device from a low power mode to be alive for a very long period of time without draining a battery that it could be running on. And then the third area, safety and security. So I keep talking about these applications, whether it's a car, whether it's an industrial environment, safety and security are paramount. So we need to be able to support that. We support the ASIL B safety. We support the hardware security module. It has hardware acceleration for AES crypto, random number generation, and we also support product lifecycle, which locks down that device when you go from development to production. Throughout the life, you can lock down progressive features.
Nice. All right, Brian. Everybody loves a block diagram. You got one for me?
Yeah, unfortunately, I guess pros and cons, some people like them. They're good to kind of show the whole thing. I'm not going to dig into too much of the details. I'm basically going to highlight some of the key areas. So as I mentioned, this is multi-core. So we're showing here the triple core version of this. This has two Z4 cores and a Z2. These are PowerPC cores. So from a processing perspective, it has a lot of performance capability with multi-core. The HSM is in the upper right. That's the hardware security module that provides all of those key security cryptography operations. It does key storage. We have lots of interfaces. We show the Ethernet below that, the Ethernet switch. There's support for USB 2.0 on the go and storage. We talked about mass storage with SDHC for eMMC or SD cards. The memory below the middle there, that crossbar switch, we see the RAM. There's 768K of RAM. A key point there is all this memory throughout the system has ECC protection, means if there's any kinds of errors, those can be seen and corrected. So
Nice.
This is, part of that safety. There's a lot of mechanisms in here that really make this a safe device, and that's one of them. We talked about the low power. There's a specific low power unit that allows us to provide those capabilities I just talked about from low power. And then finally, in the bottom, a very strong I/O system between all of the interfaces we talked about. There's lots of timers. There's multiple A to Ds. We have 10-bit, 12-bit A to D converters, 32 channels for 12-bit, 48 channel of A to D for 10-bit. We have comparators and significant amount of timers, 96 channels of timers. It's a very significant device as far as the performance, the connectivity, the memory, security, and safety.
Okay, Brian, I noticed something. What are these letters about? The B, the C, the G, what do those mean?
Good question. I know I've been showing those on several slides, so let me talk to that here. The B really refers to our single core versions of this device. So some low-end applications, they don't need to be doing that high performance. They're not doing multiple tasks. They're more about low cost. So we offer a lower cost single core version, which is the B family. We have the C, which is a dual core version. And then if you want all that performance, we can go up to the G family, which is the 3-core, the triple core version. Now, if you look underneath this, and I'm not going into detail in this chart, it's more for reference, but I wanted to show the various configurations that are available. And I talked about this being a scalable family of parts. So the first level of scalability is that number of cores. So we talked about 1, 2, or 3 cores. But we also have scalability in how much memory that we offer, whether it's, I mentioned 2, but down to 1.5, up to 6 megabytes of flash, 192K here, up to 768K of RAM, A to D converters, the number of LIN interfaces, up to 18 LIN interfaces, 10 SPI interfaces, 8 CAN interfaces, and those support CAN FD. On the high end, we support the second Ethernet with the switch, and USB also on the high end. So you can see also on the bottom, I think it's important to show the different types of packages that are supported by the various families of these devices. And on the right side, it just shows the commonality. So all those green boxes show what's common across all of those single, dual, and triple core devices. The bottom line message here is you have a lot of flexibility, pin for pin compatibility, and flexibility to pick the right level of processing, the right level of interface, and the right level of memory, and the package size that best fits your application. So it gives you a lot of choice.
Oh, very cool. Okay, Brian, as we all know, security is often an afterthought in a lot of designs, but this family has built-in security. So let's get into that. What kind of features are we talking about here?
Yeah, so security is paramount, as I mentioned, these applications, and we designed this from scratch with security in mind. The central point of the security is the HSM, or the hardware security module. This is a dedicated module within the device that is firewalled off from the rest of the device, meaning no one can get in or out directly. There's secure memory in this box that it executes from, where it stores secure keys, how it executes security services. The key here is that there is a core, Z0 core. It is programmable, and this is a key point that allows us to do those over-the-air updates, for example. So if you wanted to update security, you have the ability to do that.
Cool.
Yeah, it's a real differentiating feature because, if people add hardware, sometimes they may add a crypto and that's it. That's not secure. You need to have this firewalled aspect of it and to be able to update it in the future. Another key part is having hardware acceleration. We have modules that do the AES 128 crypto, which is, industry standard, a high level of security. We do random number generation, and we have integrated DMA that manages all the data flow within that box. We also monitor things for like temperature and clock, as in case there's some kind of issue, someone's trying to break in, we can monitor various aspects of the device and act appropriately. And as I mentioned, the secure memory is very important. This is all within that box, within this HSM, and no one outside this box can get access to this memory. So together, this provides a very secure, trusted environment that you can boot your device and run in a very safe mode and secure mode. And on top of that, we support the SHE, which is a secure hardware extension API interface, so you can write applications that communicate to it. You can't control it, you can't get in it, but you can tell it what to do through the SHE interface. And this block supports Evita Medium specifications, which is a level of security. So this is a fundamental block that's very important for this device to provide overall security for the system.
Now, you mentioned OTA earlier. Let's talk about that. I can see how firmware over-the-air updates would be really important in this space.
Yeah, definitely, especially since we're talking it's in the field for quite a while, or if you're in a vehicle that's out there 11 years plus. From an OEM point of view, or the manufacturer of these devices, there's several benefits for them to be able to update these devices over time. So OTA, over-the-air updates of that firmware, becomes very important and very interesting to people. For an OEM, for example, being able to save money on recalls. So if you have an automobile and there's some kind of issue, and last year there were 6 million vehicles recalled just because of software issues that could have been fixed without bringing your car to the shop.
Wow.
Through OTA.
Wow.
So that shows you the value of having this. You can patch bugs, critical bugs, you can add new features. It allows additional revenue for OEMs to add features down the road. And then there's demands also, though, on OTA. They don't want to impact the drivers, they don't want vehicle downtime, and they don't want to have a bricked car. Can you imagine you're doing an OTA, all of a sudden your car doesn't work?
That would be terrible.
Yeah, so you need mechanisms for that. So I won't get into too much detail here, just to mention that these devices do have specific features designed into them to be optimized for OTA, which allows it to be very fast, be very secure, to support tamper detection and flash locking. So ultimately, we can actually do over-the-air updates seamlessly in the background without any downtime of your product, right? Some products, you have to shut the product down while you do this, or you have to park your car in the garage or in the driveway while you do it.
Yeah.
This is a unique feature of this NXP device, that it can do it in the background and can support fallback modes. You don't have a situation where you're going to brick your car. There's always a way to fall back automatically also. So it's a nice feature. It's a key differentiated feature for these types of processors offered by NXP.
Okay, great. So I think I've got a handle on what the key attributes are, the applications, the overall storyline. But Brian, how do I really work with this?
Yeah, good question, because, hey, I want to be able to use this. I'm excited. I want to get this in my hands and start playing with it, build up some applications. And, we have a whole enablement support for this family, starting off with development boards. There's a full range of development boards. There's a motherboard with a daughter card approach, which gives you a lot more flexibility and breakout of connectors. That's that red board in the upper center. And we have a very low cost board, this dev kit that's in that blue board in the middle there, which is really popular out there today. On top of having the hardware support, we have the integrated development environments, full compiler support. NXP offers a complete suite of software called S32 Design Studio, or S32DS. We have a new SDK. We'll talk about that, I think, more in the future. And it's exciting because what it allows people to do is, out of the box, get a board, get the software, develop applications, and do this very low cost or free, and then have industry support from the debugger companies, the flash tool vendors, the other compiler vendors that are out there to provide support. The key message here is that this is a well-supported product. This is out there, it's mature, and it's ready to go for people today. You can start developing on this platform today.
Excellent. Okay, so what does the cost look like here? Is this a PO situation, or can I get out my credit card?
Yeah, this is one of the nice features of this and why we're seeing a lot of interest in this product, because this dev kit I talked about, the blue board, it has a lot of features on it, and it's only $39.
Nice.
Yeah, very low cost. So this is something that someone can go off and just buy today, no problem. They don't have to go through their system, go through and get approvals and signatures to buy off $1,000 boards.
Good.
$39 board. So this is ultra low cost. It gives you full access to the features. It has also the Arduino connections on it, so you could actually put Arduino shields on top. So it gives you a really broad range of expansion capabilities too.
Nice.
So you can prototype, you can put your own applications on top of it. It has a USB port. It has all the different interfaces of CAN and FlexRay and USB. And it has full support also for JTAG for doing debugging. So it's a really comprehensive system for very low cost, and people can get this from Mouser today off the shelf and start running with it.
Excellent. Now, do you have an SDK for this family?
Yeah, so that's the nice thing about it. So the board is only $39, but I have a deal for you. I have software for that too.
Awesome.
The SDK, and that comes for free. So no cost. So the SDK is something that's offered. It's on our website, nxp.com, that you can download. This comes with support for free RTOS. It's free. The nice thing, it has a complete stack. So this diagram shows a stack from the middleware down to the low-level drivers. And of course, the hardware is that $39 board with our processor on it. But it's a complete system. We have that S32 Design Studio. It's a fully GUI-based, graphical-based interface. It's real easy to use. We have this layered software architecture that works within it. And all of that support is integrated into the free RTOS. So you not only can get the board very quickly, you can download immediately off NXP, bring all the software, the development kit. There's a lot of examples and demos. You can actually start developing today with this with no issues. It's a very straightforward, easy process, and it's free.
Excellent. Okay, Brian, where should I go for more information?
Yeah, so this family, there's a lot of information that's out there. You can go through your Mouser link or through nxp.com, and everything from the real technical information with the data sheets. There's technical reference manuals that get very detailed into the nitty-gritty. A lot of times you don't need to go there because that software is there to help you, right? So we do have application notes, and those can help both from a software point of view or from a hardware perspective. How do I lay out my board? What are my recommendations for clocking this device? We actually have a community. So on nxp.com, there's also a community that you can ask questions. We have application engineers that monitor that. There's community from all over the world that get involved to help support you also. We have white papers, technical presentations. I already talked about the development boards that we have, that $39 board, the free SDK, and then we have training and support available also. So I would say it's a pretty full offering. This is mature, ready to go today, and we're here to support you.
Sounds great. Well, I think I'm going to click that link right now and buy myself a board.
There you go.
Well, I think that's all I have time for today. Thank you so much for joining me, Brian.
Thank you. I really enjoyed it, and thanks for the opportunity to talk about the MPC 574X family.
And before we go, you didn't forget to click that link, did you? There you can find more information about the MPC 574 microcontroller family from NXP. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, check out the Chalk Talk section of EE Journal right across the top. Can't miss it. Or head on over to YouTube. Keyword EE Journal.